Okay, the second part of today's class is going to be focused on nucleophilic substitution reactions. Okay, so we're getting closer to the end of this unit for SL, where we're just going to focus on a few different reactions that'll generate new functional groups. Okay, and we talked about substitution reactions already with alkanes, except those are radical-based substitution reactions. And I showed you in class and just kind of at the end of before the break, I showed you an example of one of these substitution reactions with alkyl halides. So we're going to focus on that today. All right. So any type of substitution reaction is really where I'm substituting one bond, carbon halide bond with another group. Okay. So in this reaction here, you'll see a carbon halide bond is being substituted with this cyano group to make this carbon cyano bond. All right, and then you'll see that that bromine group is leaving. That's a substitution reaction. Remember, for alkanes, we were substituting a carbon-hydrogen bond with a carbon-bromine bond. That was that radical substitution that we did for alkanes, okay? And it says over here, the bond broken is CBr, and the bond form is CCN, okay? So we've substituted CBr with CCN. Okay, in the next reaction, we're substituting CBr with water, or ends up being OH, okay? The product here is going to be an alcohol, okay, a tertiary alcohol, and HBr. So the bond broken is CBr, and the bond form is going to be COH, okay? And then the last example here, I'm going to be substituting a alcohol bond, a COH, with a chlorine, okay? So if I treat this alcohol with acid, as I showed you before, in the reactions of alcohols, we can make an alkyl halide through a substitution type reaction. Now, none of these substitutions are radical based like they were for alkanes. These are a different class of substitutions, which are called nucleophilic substitutions, and that's going to be the topic for today. Okay, so like I said, remember, this is something we've talked about before, the mechanism for radical ones, where you treat an alkane with UV light and bromine, chlorine, or whatever, and you'll substitute the CH with an with a halide to make an alkyl halide. But today we're really going to focus on reactions of alkyl halides with something called a nucleophile. A nucleophile is something that can substitute the halide in an alkyl halide to make a new functional group or a new molecule. Okay, so what exactly is a nucleophile? Well, the root of the word here, phile, means lover, and nucleo means nucleus. So a nucleophile is a nucleus lover. Okay, what's inside the nucleus? Protons. So a nucleophile must be something that loves positive charge. Okay, so something that would love positive charge would be a molecule that has a negative charge. And for the higher levels, good nucleophiles are generally Lewis bases, meaning they have lone pairs of electrons or a negative charge because they have an extra lone pair of electrons. Examples of common nucleophiles that you'll see are hydroxide, iodide, bromide, chloride, fluoride. This is ammonia, so that nitrogen in ammonia has a lone pair, making it a nucleophile. It's a Lewis base. This is cyanide. We use cyanide often to attack molecules and attach a nitrile functionality. Okay, that negative charge is the extra lone pair here. Water, believe it or not, is a very good nucleophile because it has lone pairs. Okay, when it reacts, it can make alcohols. All right, and this is hydrogen sulfide. Looks like water, but sulfur is in there, and that's how I can make a functional group called a thiol by reacting it with this. Okay, so it has lone pairs, so it can attack molecules and behave like a nucleophile. Okay, so an example reaction that was in your text, or not in your text, but here's an example reaction of a bromoethane or ethyl bromide. Okay, so ethyl bromide is an alkyl halide, and when it comes in contact with ammonia and heat, you'll get a nucleophilic substitution reaction where my nucleophile substitutes this carbon bromide bond to make a new functional group, an amine. This is ethylamine. It smells horrible, like rotten fish. Okay, releasing the bromide. Okay, now you'll see there's only 2 hydrogens here, and there were 3 before, so it wouldn't just be Br minus, it would be HBr. Okay, so here underneath you'll see just an example of the mechanism of the attack. Okay, first the nucleophile is going to attack that carbon. All right, now why is that nucleophile? Why are these lone pairs attracted to the carbon? Well, they're attracted because bromine is electronegative, so it's going to be pulling electrons out from that bond, making this carbon deficient of electrons. That carbon is going to have a partial positive charge attached to it, and this bromine is going to have a partial negative charge. So this lone pair of electrons is going to be attracted. This is called a curly arrow. Okay, curly arrows are what organic chemists use to show the direction of transfer of electrons. Okay, the steps. It's kind of like a play in basketball or football. Okay, so this lone pair is going to make a play. It's going to attack that carbon because it's partially positive charged. Okay, and as it's doing that, when those lone pair of electrons go in there, they're going to start to repel. They're going to start to repel the electrons in bromine, pushing it away. Okay, so when it attacks, it forms a transition state. This is what you would imagine is the rate limiting step. This is the highest energy part of the molecule where the ammonia is coming in. Now, once that lone pair is forming a bond, nitrogen is going to start to become positive because it's formally sharing those electrons. Okay, and the bromine is being pushed away by electrostatic repulsion. So that bond is going to break, making this bromine negatively charged. And when it leaves, it sees that negative charge, sees this hydrogen, which will be positively charged. It'll be quite acidic, and it's going to steal that hydrogen, releasing its electrons to the nitrogen to make a neutral ammonia molecule plus HBr. Okay, so a molecule of hydrobromic acid is going to come out of that reaction. And that there you have a nucleophilic substitution reaction. There was no radicals involved. The nucleophile, which is ammonia, is substituting that carbon bromine through this interesting mechanism, which I'm going to talk about later on. This is an SN2 type reaction to make an amine and hydrobromic acid. Okay, so the nucleophile substitutes the halide. That's what I talked about. And if I want to look at graphing the transition state, okay, so this molecule here is my transition state. If I wanted to graph the enthalpy of that reaction in the transition state, okay, it would look something like this. So my reactants are higher in energy, my alkyl halide and my nucleophile, they're higher in energy. And when they react, they're going to make a molecule that's quite unstable. That's my transition state. And then it's going to collapse as it's leaving, is going to make a product that is more stable, okay, being the amine molecule. All right, and that's the driving force of the reaction. So this is an SN2 type reaction where it all happens in one step. Okay, so there are two different types of nucleophilic substitution reactions that differ with respect to that transition state. So again, this transition state can be different, all right? And we're going to learn about that for the last bit of this video, okay? So we have two different types. You have an SN1 reaction and an SN2 reaction. What does this mean? S means it's a substitution reaction. N means it's a nucleophilic, it uses a nucleophile, not a radical. And 1 means the molecularity. Okay, so remember from the rates unit, this would be a unimolecular reaction. And 2 means it's a bimolecular reaction. And where does that come into play? It comes into play in the rate limiting step. So even though there's always a nucleophile and an alkyl halide coming together, in an SN1 reaction, the rate only depends on one molecule. Okay, in an SN2 reaction, the rate depends on two molecules coming together. So they're very different in terms of their rates. And we would have discovered that by doing classic rate comparisons. Okay, those classic experiments where you change the concentration of the reagents and see which one has an effect on the reaction. For SN1 reactions, only one reagent would have the effect. For SN2 reactions, a change in both reagents has an effect on the rate of the reaction. So what does an SN1 reaction look like? Well, an SN1 reaction, all right, the rate is limited only to the alkyl halide. I can change the concentration of my nucleophile, such as this OH minus. It's not going to affect the rate of the reaction. The rate only depends on the alkyl halide. So how does that work? It must mean that the alkyl halide has to break apart first to make an intermediate, and that would be the slowest step in the reaction. And that's what happens. Okay, so here I have a tertiary carbon, 1, 2, 3. This is a tertiary carbon. SN1 reactions really only happen with tertiary carbons because when it breaks apart, it forms a positively charged carbon. And that positively charged carbon needs help from its neighbors. It needs donation of electrons. Okay, if there were hydrogens attached here, the hydrogens couldn't donate electrons. It couldn't stabilize that positive charge. So SN1 reactions only happen with tertiary carbons. Okay, that's a very important thing. I'll write that here. This tertiary carbon is really, really important. Okay, so that would be a quite stable intermediate. And once that forms, now the OH minus can see the positive charge and attack. Okay, another reason that the OH minus wouldn't react is because it has no room to get. If I built this molecule, which unfortunately you can't with our modeling kits, you would see that there would be no room for this OH molecule to get in there and attack that carbon. So it needs to wait until that bromine ion leaves to make this molecule, which is flat. It's trigonal planar. There's lots of room now for that OH to come in, okay? So that's why tertiary molecules, tertiary carbons, only react through an SN1 mechanism. And the SN1 mechanism forms a very stable intermediate, the carbonium ion intermediate. It's a carbocation, okay? And then the product would be a tertiary alcohol. All right, so it's a unimolecular reaction where the rate is directly proportional to the concentration of alkyl halide, has nothing to do with the hydroxide, okay? And if I was to look at the reaction mechanism and the energetics for the higher levels, okay, it would form a stable transition state. So it goes, it can sit there. We could isolate that if we're lucky. And then that transition state would then react with another hydroxide to make the product. Okay, that's very unique for an SN1 reaction. For an SN2 reaction mechanism, it's a little bit different. Okay, SN2 reactions happen primarily with primary and secondary carbons. Okay, in that case, the OH has room to see that carbon that's going to be partially positive charged. It has room to get in there and start attacking. All right, and if these are carbons, it wouldn't have room. So here I have methyl bromide, which is a primary carbon. All right, in the reaction, the hydroxide is going to see that carbon that is partially positively charged, and it's going to attack. And as it's attacking, it's going to form this interesting transition state that's high energy. Okay, the hydroxide is going to be repelling the bromine atom, or the bromide atom, which becomes a leaving group. Okay, and then that bromide is going to see the extra hydrogen that was here, and it's going to steal that hydrogen to make HBr. Okay. Actually, sorry, disregard what I just said because I'm reacting it with OH minus. So my product is going to be Br minus, okay? So in SN2 reactions, because we're making this interesting backside attack and knocking it out, it's kind of like a chain reaction, all right? The rate is dependent on both the concentration of my alkyl halide here and my nucleophile, okay? So if I change concentration of the nucleophile, the rate's going to go up. If I change the concentration of the alkyl halide, it's going to go up. All right, and that's called a bimolecular reaction. All right, so the important part of that is we don't have any carbocation intermediate. All right, and if I was to look at the energetics of the reaction, it all happens in one step with no intermediate isolated. Okay, when we talk about some interesting isomers called stereoisomers or chiral isomers, we're going to come back to this because you're going to see that there's a very unique situation that happens between SN2 and SN1 reactions. Okay. Last thing I wanted to talk about is the effect of the nucleophile on the rate of the reaction. Okay. When we react, if I was to react some molecules with iodide, bromide, chloride, and fluoride, I'd find that the rate of the reaction would be fastest when I react with an iodide nucleophile, then a bromide nucleophile, then a chloride nucleophile, and then a fluoride nucleophile. And I bet you guys can start to figure things out just by that list. And it's definitely based on ionic radius. Okay, since the ionic radius of iodide is bigger, okay, it means it can see the carbocation or the positively charged carbon from a further distance. Okay, the fluoride ionic radius would be very small. In order for the fluoride to react, it would have to get a lot closer than the iodide would. Okay, so what we say is iodide is a lot more polarizable. The electrons are juicier, and they're able to react from a further distance, meaning that the rate of the reaction is going to happen quicker. Okay, the same thing is true for the alkyl. If I had an alkyl halide, so if I had an iodide that's attached to this molecule, okay, the iodide is my leaving group. Okay, meaning that is going to leave the reaction. The iodide is a better leaving group than the fluoride for the same reason, is because that it has a very large radius, okay, and that iodide is sitting a lot further out. And those electrons, because it's electronegative, it's able to pull the electrons further away from this carbon atom, making it even more available to attack. Okay, that's just because of the bond length and the polarizability of that iodide. Even though fluorine is more electronegative, that bond length is so short, okay, that even the electrons that are around fluorine are still around that carbon. That carbon is not as positive charge, and it's not going to be calling for an OH molecule, a negative anion to come and attack it because it already has electrons around it. That's pretty interesting, something that we wouldn't think about just based on electronegativity alone. Okay, so this is just kind of a summary of what you would read in your book. Okay, it's not probably the best thing to learn from, but hopefully it helps.